Hello and welcome everybody. And thank you very much for joining us today on our webinar on fraud detection with graphs at Danish Business Authority. My name is Alexander Erdl. I'm your host today. I'm with the EMEA marketing team, and I'm super happy that so many people joined us for this session today. With me today, I have my colleague Rick van Bruggen, who will give a short intro to today's topic, fraud with graph databases. And then I'm very excited about the star of today's webinar, if you don't mind me to say so, Rick, is Marius Hartmann from the Danish Business Authority. Marius works in data science, in the data science unit there, and tries to prevent or aims to prevent fraud. He is responsible for the design of the ML data platform at the Danish Business Authority, which revolves heavily around the usage of graph technology. So this is basically giving you a good overlap between data science, machine learning, and fraud detection and prevention. So I think this is a great insight, hopefully, for everybody. Quick basics overview. We will record this session, of course, so you will get a video afterwards. You can watch at your own time. If you have any questions, please use the chat window on your right or the Q&A panel. We will try to make some time at the end and answer one to three questions who came in through this panel. So please don't be shy and use it whenever something pops into your mind. But yeah, that's enough from me. Rick, the virtual stage is yours. Thank you all.
Thank you, Alex, and good morning from my side as well, everyone. Happy to be here. Happy to see you all virtually. Great opportunity to talk about some amazing use cases for graph databases, graph data science, and that's what we'll do this morning. I'm going to do a quick introduction, also kind of try to explain how this technology fits, right, and how you can use it for this particular use case before I hand it over to Marius. And like Alex was saying, happy to answer questions at the end. Don't be a lonely document, right? And please use the chat functionality to the best of your ability. It makes it nicer for everyone. Good, let's get going. Well, I mean, I kind of want to start by leveling the ground here for everyone. If you're not aware, why and how a company like Neo4j, this obscure Swedish-American acronym named company, is active in the wonderful world of fraud detection. Well, that's because we've been at this for quite some time. We've been at the graph space for quite a few years. Emil, Peter, and Johan started our project, the open source project, back in 2001, right? So that's 20 years ago, crazy. And the commercial product and the commercial company has really been around since 2009. I've been around here. I've been working for Neo4j since 2012, and I've got all the scars and all the smiles. So it's been a great journey so far. And what we've been doing is really we've been trying to advance the industry, the data industry, if I may call it that way, to better use this very old concept, which is the concept of networks, of graphs, right? We want to use that more in depth, right? We have created a new kind of graph, a new kind of data structure to better deal with graphs, the property graph. We've created a query language to better deal with this data structure, Cypher, and now being standardized as GQL. And I think we've got the experience of literally thousands of users and customers that have been working with us to really show the world, what you can do with graphs, right? Lots of big organizations, but also lots of smaller organizations that use Neo4j, either on-prem or in the cloud, wherever you want to use it. It's really been adopted quite widely these days. And the fundamental premise that we have here and that we want to advocate for is the fact that, when you have all this data, the connectivity between the data, the relationships between the data is oftentimes as important as the data itself. It's a little bit of a high level remark, right? But I think it's a very fundamental remark, right? Because you can see this everywhere, whether you're talking about social networks, networks of people, or transaction networks, or knowledge networks, the links between the data elements, the references between the documents, the friendships between people, the sequence of transactions, these things matter. They are very important and they are very valuable. And they've been a little bit underestimated in previous decades. So what Neo4j really is advocating is that we really take a look at this, and we really take a look at these relationships between data elements, because they hold, potentially hidden, but they hold business value. Right? And there's a lot of different ways that you can look at that. And it's been very transformative in lots of different domains. It's actually quite of a horizontal thing. You can see it in so many different industries. We actually have these little stickers that say graphs are everywhere, because we really think it's, omnipresent. You can see it everywhere. It's very transformative, whether you're looking at data-driven discovery and innovation, or data integration, or AI and ML. You will see the graphs, you will see connectivity between data elements pop up everywhere. And that's why we've been chipping away at, and we've been building this thing called a graph platform, right? And at the core of what Neo4j does, you will always find this fundamental piece of software infrastructure called a graph database, right? You need to store the data somewhere, right? You need a repository to work with graphs. But in order to get that value, in order to see those transformative business applications of graphs, we need things around that. We need things like integration tools and visualization tools and development tools and, analytical tools. There's a lot of components that really should surround that graph database to get to value more quickly. And that's the entire vision. We've been chipping away at this for a long time. Core thing is still the database, lots of things around it. In the past 2-3 years, I think we've seen something so fascinating in our industry, which is that, we've been starting to see the emergence of a new field around graphs, around networks, which is really what we call graph data science. And I mention it because it's very relevant to what we are going to see later on, fraud detection with graphs. This graph data science component is what is going to enable us to uncover what we don't know yet, to uncover new patterns, to leverage new insights, right? It's going to tell us, based on structural analysis, number crunching, and looking at the nature of the networks that we are storing in our graph data platform. We're going to look at that and we're going to see, okay, these parts are more important. Those parts are belonging together. Those parts are similar to one another. That's what we're going to be looking at with data science. And it's going to give us a lot of more predictive power. It's going to give us a lot more possibilities to really leverage those relationships and see things that we couldn't see before. Right. And very importantly, and I want to stress this, it's usually based on the data that you already have. We're not like inventing new data here, right? We're not adding new data here. No, it's usually the data that you already have that actually contains those relationships, contains those links between your data elements, and we just surface them. We just analyze them and surface them for you. Right, so it's a super powerful thing to do, and we're going to be applying it to this fascinating domain of fraud detection. Catching the bad guys, catching the fraudsters, right? It's just one of those examples of, graph applications. I want to stress that, we're going to do lots of other webinars as well, and we have done lots of other webinars before around other use cases. Right, because at the end of the day, graphs are kind of applicable to anything. You can see them everywhere, but reality is that people are going to adopt this one use case at a time, right? They're not going to like implement and overhaul their entire infrastructure all at once. They're going to, look at the most valuable use cases first, and then, implement that, see how it goes, iterate over that. That's the way you implement new technology at the end of the day. Fraud is one of those use cases. And it's not just us that thinks that fraud is actually a really important use case for connected data for graph databases. This has been confirmed, the world over by people like Gartner, but there's lots of, industry specialists that have highlighted this as well. And what Gartner has highlighted, and the report is linked here, is that, you can kind of see a scale of sophistication in fraud detection, in fraud analysis, right? At the most elementary level, we look at endpoints, we look at individual data points, individual users, individual transactions, individual policies, whatever they might be, and we analyze those. We really look at the details of those, right? Gradually, however, you can see that people are adding scope to their analysis. They're making the analysis broader, and they're not just looking at that individual endpoint. They're also looking at, the account that endpoint belongs to, or the other channels that endpoint has used, or other entities that have been linked to that endpoint. So the scope of the analysis has become wider, right? So there's a lot more integrated in connected fraud detection these days. And the way to think about that maybe is to look at the difference between something we call discrete data analysis, right? Where, if you apply it to the fraud use case, right, we have this band of transactions or people or whatever, or that are fitting a normality profile, some kind of a standard profile of a transaction, of a person, of a car, whatever it might be that you're analyzing, and it fits the bill. It kind of fits within the realm of normality, right? And we look at that and we say, okay, everything outside that we're going to analyze, we're going to investigate, but the things that are within that band, we're going to assume that they're okay. Right? That's what we call discrete analysis, right? Because it looks at those individual data points. It looks at those individual data elements, and it tries to infer, is this something that we need to investigate, yes or no? The advantage of that is that it's super simple, right? It's super quick also. You can do this, you can automate this in a really easy way, right? And it will probably stop some rookie fraudsters, no doubt about that. But, will it also stop the more sophisticated, high value, important fraudsters? That's the question, right? And which is why, we're evolving towards this more sophisticated form of fraud analysis, which is connected. It links things together. It doesn't just look at the outliers. It also looks at the cases that are within the realm of normality, within this range of normality, but it also looks at the links between them. It doesn't just look at the individual transactions, the discrete transactions. It looks at the links between them and tries to see if potentially there might be something weird with that. There might be something that we need to investigate, right? That's what we call connected analysis. And that's the type of thing that we try to enable with Neo4j. We're a connected data store. It's a connected data platform. We're all about making these relationships first-class citizens. So as a consequence, what we want to enable and the value that we want to provide to our customers is really that you can analyze not just the outliers, but also the seemingly normal transactions or people or whatever it is that you're analyzing, and look at the sophisticated and suspect patterns that are a little bit more connected to one another, right? This is traditionally quite complicated. We have struggled with this as an industry. As an industry, we've not been able to easily implement this for a bunch of different reasons. But the reality is that the infrastructure wasn't optimized for it, right? So traditional data stores are not optimized for treating the relationships. And I guess the graph data platform that Neo4j advocates is very much optimized for this, right? That's why we think that the challenges that people have been facing with connected data analysis can be addressed with technology like Neo4j, right? We know how to process large amounts of relationships. We know how to do this on a continuous basis. We know how to do this in near real time. And we've got a bunch of cases that will highlight that to you. So I guess that's the premise of how we look at graph-based fraud detection, right? It's that we really want to enable a more scalable, real-time, and relationship-centric analysis of potential fraud patterns. There's a lot of functionality in the platform around that. There's a lot of case studies around that. There's things like fraud ring analysis that has been extremely popular in insurance industry, for example, but also with government organizations like the Danish Business Authority that has been implementing this at scale as well. So that kind of concludes my introduction. I think this is a really exciting topic. I'd love to hear more of your ideas and your questions today. But with that, I'm going to pass it to Marius, who's going to present the Danish Business Authority, the DBA, as we call it, their case study right now. Thank you for paying attention. Appreciate it.
Thanks a lot. I'm really pleased to be here today. I'll be talking about graph within the Danish government, how we use graphs to detect fraud, specifically in relation to businesses at the Danish Business Authority. My name is Marius Hartmann. I work as a chief advisor at the machine learning lab, which is a part of our digital innovation unit within the authority. And we strive to stay ahead of the curve with interesting technologies. I've been working for quite a number of years within IT, and the machine learning lab is around 15 people with various background, mostly natural sciences and computer science background. Now, the Danish Business Authority is really has a two-purpose goal. One is to create the necessary framework for growth, so so that Denmark is an interesting market to start your business in. But it's also we also have the task of creating a level playing field, so the risk of committing fraud is present for the fraudsters. So you can say that we always have to balance out when are we applying too much regulation and when is that affecting the growth of the healthy businesses. So we definitely don't want to disturb responsible businesses, but we want to get rid of the fraudsters. So one of the things we've became involved in 2020 was the COVID-19 compensation schemes. Denmark experienced a nationwide lockdown in March and established 4 compensation areas in relation to wages, in relation to large events, in relation to independent businesses, and the normal expenses of a company. So we have these different 4 areas, and of course this is something that affects not only the Danish authority, but also the tax department and other actors within the Danish government. We've received so far in excess of 230,000 applications, and we've paid out around 3.5 billion euros, so quite a sizable sum for a small country like Denmark. Now, the problem of doing fraud detection within a state is that the way a government is distributed among different ministries and boards, you have sort of situation where it's naturally designed to be data silos across the government. And this presents a barrier for the different authorities in that you're supposed to regulate only your area of interest naturally and protect the interests of the citizens as much as possible. But fraudsters are not part of that plan, so they are able to move across the different areas of responsibility in order to commit fraud. Now, this is of course because they are motivated by money, so they are not really adhering to the way the state was designed and divisioned. So the problem of fraud detection is that no one really has the big picture, because the Danish authority has received legislation that enables us to get data from other authorities as long as it's part of our control effort to detect fraud. So suddenly we have access to other authority data that is of interest in a fraud investigation. And I'll show you some of the compensation scheme controls that we have built on top of that. And afterwards, I'll explain a bit about, well, how did we achieve this? So you can say that one of the major problems of detecting fraud is to distinguish between what is just erroneous or sloppiness apart from the company side. Is this just an error, or is this an intentional anomaly in order to commit fraud? So there's no exact way of determining this, so you have to look into a lot of different factors. So we think of it in the normal sense as it presents some kind of risk. So the first model we've built that really utilizes the graph is our ability to use multiple features in order to calculate a risk. And such features can be the activity level of a company. How many times does management change? How many times do you change the address? What's the nature of the address you change to or from? And a lot of other bits of information that individually are not really significant. But when you get the picture of a company as a whole, it presents you with information how that company is placed in a grid of all other companies, so you can sort of see who's an outlier in the range of all companies. It sounds a bit strange, and I'll try to explain this better later on. So one of the things you can then utilize once you've done a risk calculation of the individual company, you can then use that for purposes in which you may need another bit of information. So in one of these schemes, we are tasked with looking into a certain type of scheme where the necessary data is not yet present. So, I mean, how do you control something which isn't there yet? You must remember that all these applications needed to be controlled both at the time of the application and then during the phase we are in now, where we're doing the after control, where we go through the numbers once again. And now we have a different data because we have all the application. But at that stage, you may be looking at a bit of information. You don't really have that yet. So you can do a proxy estimation based on what you know. So in this case, we were looking into some accounting information where we actually used the one of the actors presented with the company and their immediate network surrounding and all the risk scores associated with their network. So now you can begin to see how you can combine information that you have in the graph in order to gain more advanced calculations of risk. So one of the simplest way to use a graph, and one of the benefits a graph poses to our work is simply data as a commodity. You know, when data is present, you can just combine and use data in various ways. So you can do calculations that are not overly fancy, but are simply possible because you have the data there, and it's easy to combine different factors of what you wish to investigate, because you have all the data collected and available to you. This is something that's normally a bit of a pain, just the basic access to data, to have it normalized, to have it accessible in a format that's usable. Pretty much the graph takes care of that, not because it's necessarily the most correct way to access that kind of data structure. I mean, a relational database is wonderful, but it's a selling point that the data is just available. In order to have the accessibility to data and a low time to market, because some of the problems you're trying to solve, some of them require you to be hasty. You need to be able to answer now, and some things can wait 12 hours if need be. So we have some ways of utilizing, now that we have all the data. You can say we already have the background data of companies, but at the present stage we also have the immense amount of data related to the applications themselves, in excess of 200,000 applications, more than 1 million documents associated with those applications, spread out over, I think it's 175 types of applications. So there's a quite rich variety and granularity in the data that we can now utilize by means of graph, and again look into multiple features at once, look into how the individual case we're looking into relates to other cases. So it's a way of combining your ability to cluster cases and just simply have access to information relating to a particular case. So right, some of these things could be related to application deadlines. When did people, the businesses, when did they apply? And that can also be a factor in finding anomalies in your data. So we this is an example of how you can have readily available information concerning an application. So this is a view of a case that has 32 related cases, and these are all part in some way of a complex of applications, not necessarily fraudulent, but it's just a way to illustrate that you can quickly bind together information that you have in your system, and you can use that for various things. Here the same 32 cases are presented with the IP address that was used for those applications, and you will see that we have some free-floating parts of the graph on the bottom, where you can see that, well, within the same time period, that IP address was used also for other applications that are not formally related to this type of applications. So we have some other businesses applying within the same time frame from the same IP address, and this can be quite normal, and this is actually one of the ways a graph is also beneficial to eliminate the risk of fraud, because some of these cases, when you look into them, you'll find that the companies responsible for the application we see on the bottom were actually related to the other 32s by means of co-ownerships of a third company by these actors around these networks. So the graph can make you discover things that are anormal, but it can also just eliminate your idea that something fishy is going on. Now, how do we use graph? And you have to think of this, that when we look into a company, there are really no two companies that are similar. I mean, they are all constructed around the same legislation, but they all vary in terms of the person's part of management, the address, the code that's being used for the company registration. I mean, the area of a business that company is operating within. So you can't really take two companies and say, okay, they're the same, but one is abnormal. Also because of the other factor that companies change all the time. They change address, they have changes in management. So what we discovered the graph is really useful for is the ability to compare snowflakes, to compare companies based on their differences. That when you take a particular company node, you can then extract the information around that network and take that as a view of that company at that point in time. And you can use that to compare that with all other companies, in spite that they are all different to this particular company and to each other. So this would be rather hard to do with any other database, because the amount of views into the data is really equivalent to the number of businesses, but also to the points in time where you want to make that investigation. And as they are all continually changing, that becomes a rather chaotic model, almost a living data entity. And that's where a graph is rather handy for extracting and discovering that type of information. So yeah, we've built a knowledge graph within the Danish Business Authority. It's based on our access to other authority data. It contains all the around 800,000 Danish businesses with a full history of all companies dating back to the 1700, I think the oldest company is. And we've combined that with all the annual reports, the experiences from other authorities, such as the tax department, what's the VAT history of these companies, what's the experiences of other authorities in relation to controlling these companies, and the actors part of those companies. And of course, as I've already mentioned, we have a lot of metadata as well, IP addresses, that sort of thing, and a lot of our own experiences with regulating companies and case handling companies. And we also have model data put back into the graph, and that is something that's proven quite valuable in relation to also governing a lot of machine learning models. So right now we have, as it says, 400 million nodes and 700 million relations. It's growing quite fast. At the moment we're growing by 100 megabytes per day in the graph. Now the reason that we needed to take the path of using a graph database is really that we have the task, since we at the authority run the Danish business registry, we sort of license a company to form. And that makes us the sort of first line of defense against fraud. So if we're able to stop a company from being registered, we've already then prevented a lot of fraud that otherwise would be taking place. But that's also a very hard question to answer. Is this going to be a fraudulent company? Is this company being registered with the sole purpose of committing fraud? So in order to understand that and to make the distinguishing point between what's an error and what's a fraudulent, purposeful action towards authorities and other companies, we sort of formulated that we wish to understand business life cycles and the factors affecting these. And I've already mentioned a lot of the factors that can be influential in relation to getting knowledge from companies based on their timeline. And the other things I briefly mentioned was that we also put machine generated data back into the graph. And this is because we really a dual purpose. One, we like to keep our machine learning models as simple as possible, because you don't want to govern a lot of models that essentially do the same thing, because you run the risk of having discrepancies between their understanding of the world or the business area they are working with. So you don't want two models that deal with a particular parameter but concludes different things. That would really mess up your ability to work with these things. So by writing back to a persistence layer, we can sort of keep our models slim and build them in such a way that they're good at one thing. But the other part that this is beneficial is that, well, you're basically turning your graph into a common feature store, or at least at a rudimentary level. You can share the experiences of specialized model with other models, and of course just a data exploration. So one such case would be, we have a model looking into the identification papers of management from foreign actors, part of Danish companies. We have a model that looks into more like the economical foundation of a company where they state some assets that may be erroneous or fictitious. And we are also using a lot of NLP models, as we have a lot of unstructured data in Danish authorities. So there's a lot of places where an auditor or a company will write something that we need to be able to understand. We receive around 230,000 annual reports from Danish companies, and those are all quote-unquote read by a machine learning model looking for comments made by the auditors. So we're sort of weaponizing what we already know, but in a way that it's accessible to computation. And you can see that by standing on the shoulders of other models, we're sort of able to utilize that information as a first line of defense when we need to very quickly estimate whether a company is being formed or registered with the purpose of committing fraud. Now that's would take quite a lot of processing power and data to compute, and it only takes a matter of minutes to register a company. So we need to be really responsive there. So I'll just explain this principle of model to model. Here we have a tiny little graph showing in the middle we have the pineapple company which is being formed, and we need to have an idea of what's the risk of this company being formed. We can follow the arrow and see that it's being managed by John, the director. But we already know from John that he's also part of management of the banana company. And this is where we have the gray and the red dots, because the gray dots, they represent models that have input some data back into the graph by going through the identification papers, for instance. So on the right, the ID model has stated an observation that the ID document of Jill, whom was part of management with John in the banana company, is actually fake. And perhaps the banana company also stated some fictitious assets, and even there's something in the annual report that looks fishy from the auditor. So now that we have all this background information, it puts the pineapple company in another light. And it may be that we, based on this information, would like our colleagues in the control department to go through this company formation manually. Of course, we never automatically decide anything. It's always with a human in the loop. Now, because this is an immense data structure that's quite powerful, of course, we need to consider the ethical dimensions of this, and we've formulated a lot of formal ethical principles, but I'd like to also address some of the informal principles, because we've needed to make the entire part of our data within the graph to disclose that it's all sensitive data, so it's kept separate from any other system at the authority, because it's quite a large part of data silos that have suddenly merged into this giant knowledge base. So some of our informal rules concerning ethics are also actually based on effectiveness. So one of the reasons that we don't make lists of people is that it's unethical to keep a list of bad guys and a list of good guys, because who would like to live in a society like that? But it's also highly ineffective because of the time dimension, because people can be quite good until a certain stage, and then they can be quite good as again. So we need to look at the time. It's not just a 0-1 problem. And of course, we can only do calculations when there is a business purpose. So one of the necessary steps taken in order to govern all this data is that we always have an idea what data is being used for. And this is also part because we wish to be able to monitor if the precision is right. Are we actually achieving the purpose we set? We sort of used the data for initially. Is that having a business effect that we wanted, or has it changed since then? One of the real dangers of working with machine learning is that models are good at something with a purpose, and suddenly that purpose changes, and then you need to really reevaluate what you're doing. So we need to be able to monitor machine readable monitoring of our data usage. We cannot really rely on when we made that initial model that we stated that we were going to behave, because things change over time. We cannot foresee the developments at all times. So we need to have this interpreted continually by our monitoring systems. And of course, this comes back to always being able to answer the question of why is this model? Why does it exist? Is there a business purpose? What data is it using? And in the end, this kind of reporting power is also in order to keep management accountable, because that's the chain of command in any organization, that management really has the say on what's going on. So I'll just quickly mention that this data-driven ethics, we're actually supporting our ability of having real or near real-time data events with the usage of messages. So we are now doing our second installment of our data governance, data ethics infrastructure, which, as you can see on the image, output a graph of all the events that's going on. So this could be a data ingests that starts with some artifacts at source and a legislation in part of ingesting that data. Then we can see or trace every event that based itself upon the initial events, in order really to play back when we are in the situation where we actually used data in a case handling. We can sort of rewind all the events and see, well, who really touched the ball on this case, so we can trace back all the data. And this is also part of our evaluation processes that we go through and evaluate what our models do. So in order to round up some of the principles we're working from, well, we have the luxury of being able to connect other authorities' data. We have the near real-time capability of reacting, so we can sort of chop up some of the problems and pre-calculate some of the things we wish to ask at a later stage in our registration. And of course, the necessity of understanding business life cycles relies on the network analysis we continually need to make. And also we're data greedy, I like to think, so we need more data from data all the time. And this is based mainly on our machine-driven insights. So this never goes down without direct collaboration with our domain experts. We're always working in different legislation parts of the business authority or other authorities, and we need to have a sound understanding of what data represents and why processes are taking place. And we've also affected the way we build our infrastructure, that we're now heading towards a more DevOps-like setup with an idempotent way of running our infrastructure as code. So we are certain that we can recreate the situation of a particular model and the data it was trained on, and how the world in terms of data looked at that point in time. So we like to think that the effect of all this is that all companies are subject to control. Every time they make a registration in one of our systems, a model will react to that and recalculate, for instance, a risk scoring, or look into identity papers, or if it's an annual report, then the model will chew through that one. But we hope that we really achieve full transparency by means of our metadata layer, of the event layer, and sort of what we like to call keep humanity in the loop.
Great, thank you, Marius. I think that was very, very cool. And we have a lot of questions for you in the chat room. I do want to point people to a few additional resources that they can find online. We will publish these slides to everyone that registered, so they will find these links in the material as well. But maybe we can just take a quick look at some of the questions, if that's okay for you.
I just skimmed through. NLP means natural language processing. The
fraud detection, the risk assessment, we use the XGBoost algorithm. So the risk is comprised generally of the experiences of existing controls of that company, and the risk of that company, the life science of that company is this heading towards bankruptcy. So you could say that a lot of this information could certainly be reused also for providing better service to companies that are looking like they need some help. So those are the ones I remember. I'm not wearing my reading glasses, unfortunately. So I have to
maybe I can try and ask you a couple of those. Would that be okay? I mean, there's a couple of questions. We won't be able to answer all of them. If necessary, we can always do that offline. But there's quite a few questions that ask you about data loading. Can you talk to that? How did you load the data into your graph, or how do you continuously do that?
Yeah, in our current setup, we're using Apache Kafka as a mediator between our source systems and the graph. And the graph is populated by, I think the term was handcrafted Java adapters. We are now migrating that to a more regular data pipelining tool. We are moving to Apache Airflow, which is caused mainly because we want to run not one graph, but we want to run several, each for a specific purpose. And this is also caused because the way we use the graph together with machine learning now is really we do a lot of the computation external to the graph, but a lot of these graph algorithms are showing us some sort of built-in logic within that structure that we wish to utilize. So we want to have some more views of the same data, but in a more appropriate structure in a graph for that type of computation. So you could argue that we're sort of moving from seeing the graph as a persistence layer, but more as a compute node, more as a machine learning model in itself, just a very big one.
Interesting.
I saw one of the questions was also if having two models disagreeing on an output, if that's necessarily a bad thing. Well, it's not a bad thing. Is in a typical A/B scenario, but it would be a bad thing as a public authority to have different ways of relating of upholding the law. So we sort of need to decide on what it is we think. And also if you had, for instance, a chatbot advising a company from one perspective and another bot punishing or enforcing controls on the same company from a different perspective, we would have all sorts of problems. So it's a kind of also a governance issue.
Understood. There were a couple of interesting questions I thought as well about your team and how you work with your team. Because obviously you can do this as a one-man band in a corner somewhere, but would be interested to understand how big is your team, how many people are working on it, how did you build it up? Can you talk to that a little bit?
Yeah, we are 15 people, and we have a high degree of autonomy. Apart from our production systems, we have our own lab servers where we can sort of restore a production graph and enrich it. So we have a fairly autonomous development environment where we can sort of build the next generation of the graph we wish to have in production. We're also very Linux driven, and in a normal enterprise, you get your Windows laptop, no admin rights. We have a secondary laptop with running Linux. So together with our servers, that gives us quite a lot of agency in terms of running our own experiments and models and graphs to speed up the production pipeline. And that's also why we are moving into the more continuous integration, continuous development cycle in DevOps, as this is also moving your idea of how to maintain a database, because you with the insights you get into your data from the graph, you realize that the information, the amount of information is growing all the time, specifically because the structure of things becomes an information source in itself, as you were hinting at in the beginning, and that's incredibly interesting. And we're also seeing that causal inference is having a huge revival right now, and that would certainly be interesting to also investigate by means of graph.
So there was another question related to that. Was have you got any kind of an estimate of how much effort in person days and stuff like that you put into putting this system together? And then, if I may add a personal question to you, how did you justify it? Were there measurable outcomes that you were able to point people to and say, okay, this is why we need to make that investment?
Yeah. Well, we've been having graph in production for a couple of years, and it was certainly requiring quite a bit of pre-analysis to get the business registry transformed into graph. We had a few tries actually. So the best way of achieving your goal is really to try a few times, because it also requires you to think about what are the moving parts in your data, what's the defining features of your data, in order to see how things are related. But also, when you wish to have the aspect of time in your data, you need to have some additional nodes within, so you can have that quality. And it's also actually our justification part is from one of the simplest but very powerful features of a graph is to discover whether things are connected or not, and the nature of their connectiveness. And it's when speaking in the term of graph, it's very it's almost primitive to have that ability, but it's an ability that's incredibly hard to achieve in databases where you have to connect a lot of tables, because it takes computationally an incredible amount of time to do the same simple calculation.
Great. Maybe one more question before we wrap up, and I know that there's a lot more that we could talk about, but it would probably take a little bit too long. But you talked a little bit about like the ethics in your talk, right? And how do you deal with that? Someone was asking, and I was asking myself the question as well. How do you deal with privacy? The sensitive data that
definitely,
private. Any comments on that?
Yeah, we've been through a formal vetting of this system from a legislative, from a GDPR perspective. And one of the choices I made from the beginning was to keep this data isolated from the rest of the authority, because we are allowed to work this way because of the control purpose, not any other purpose. And also due to the power of the connectiveness in data, I took the choice of marking all this data as sensitive, because if you have one node in one end, it's naturally connected to some more sensitive information. So you can also argue that this is a great tool to de-anonymize information that's readily available in the press. When you have this, there's almost no way you can mask information in the outside world from this kind of data structure, because you have the luxury of taking multiple perspectives into data. So it's also moving your realization that, well, data is really sensitive, all data, if you have a powerful data structure.
Great. I don't know if Alex, I imagine that you're still on the webinar as well. There's still a lot of questions outstanding, but I don't know, how do we want to deal with that?
Yeah, I think we need to wrap it up. We will collect your questions. We can collect them and forward them to Marius, and then see if there's some way we can give you a condensed answer. But you can reach out to us all the time. Obviously, if you have something you want to talk about, talk to Rick, talk to anyone from the team, and we will try to help you. But in looking at the time, I think it's probably best if we
won't be able to get through everything anyway.
Exactly.
But,
yes.
yeah.
It's yes. Yeah.
From my side, thank you, Marius, for doing that.
Yeah, and thanks for the great questions. Really good questions.
Yeah, exactly. Thank you, Marius. Thank you, Rick, for taking the time and for presenting your use case, Marius. And thank you all for attending and asking so many questions. So yeah, it's really good. And we hope to see you soon at the next webinar from Neo4j. Thank you all.
Bye.
Bye, everyone. Bye.